Welcome to this overview of the Centre for Nanoscale Systems' Imaging and Analysis facility. Over the next few minutes, we'll give you a taste of the types of analyses that are performed at our centre. Our goal is to enable characterization of hard and soft materials over several length scales from the macro scale to single atoms. We achieve this by providing equipment, training, and support over a variety of techniques, some of which are highlighted in this video. Micro-CT, also known as X-ray microtomography, is used to generate 3D renderings of physical objects. We can produce virtual models with a spatial resolution of up to 500 nanometers. Big advantages of this technique are that it is non-destructive and can be used on a diverse range of specimens. X-ray photoemission spectroscopy, or XPS, is used to study local changes in chemical composition and species valence at specimen surfaces. Depth profiling adds an extra dimension to this technique. The Optical Spectroscopy and Microscopy Lab accommodates experiments with ultraviolet, visible, and infrared photons in a variety of ways. The highly flexible Horiba spectroscopic microscopes allow for Raman scattering and photoluminescence measurements. They can accommodate a wide variety of samples and are often used to produce chemical maps. The X-Polaris system incorporates the Citoviva dark field hyperspectral imaging spectrograph in addition to its Raman spectrograph. The CNS technical staff are here to help and often assist with custom experiment designs. There are two Fourier transform infrared spectroscopy systems. The IS50 has a diamond ATR crystal that can be used for solids, powders, and liquids with very little sample prep. It has both a mid-IR and far-IR beam splitter, allowing measurements from 1.5 microns all the way to 100 microns in wavelength. The Bruker-Loomis FTIR microscope allows for chemical mapping of samples using ATR, specular reflection, or transmission mode. It has a germanium ATR crystal with a 120 micron diameter tip. The collection area can be apertured down to collect data from smaller areas. The CNS staff can also assist in advanced spectral data analysis, like the principal component analysis of FTIR data. The Carry 7000 UV-Vis near-infrared system has an integrating sphere for measurements from 200 to 2500 nanometers. It also allows for variable angle reflection measurements, polarization mapping, and transmission measurements. The spectrofluorometer can be used to make steady-state photoluminescence measurements on liquid or solid samples from 200 to 800 nanometers. CNS also has a multimodal multiphoton microscope. This microscope is connected to a deep-sea femtosecond laser that is tunable from 780 to 1300 nanometers. It also has a fixed 1040 nanometer output beam. The tunable beam can also be used for second harmonic generation mapping, polarized second harmonic generation mapping, 2-photon fluorescence, and 2-photon time-resolved photoluminescence mapping. The fixed beam and tunable beam can be combined in time and space to be used for coherent anti-Stokes Raman microscopy and stimulated Raman scattering microscopy. More traditional optical microscopy techniques are also available. The microscopes can be configured to accommodate a variety of samples, including experiments in microfluidic devices. We have a selection of prototyping tools, characterization tools, and wet bench facilities, along with a dedicated biomaterials space. The biomaterials space houses our serial sectioning equipment, which is used to make samples for transmission electron microscopy. We also have a separate electron microscopy sample preparation space, which is primarily used for preparing hard material specimens. Our scanning electron microscopes are used to characterize a very diverse range of systems, ranging from bugs to nanomaterials and anything in between. We have secondary and backscattered electron detectors, variable pressure mode, and cryo-SEM available. In addition to having various SEM imaging detectors, our users can perform more advanced elemental characterization through EDS and/or the higher precision WDS spectroscopy techniques. Near-surface crystallographic information can be mapped with our EBSD system. Dual-beam focused ion beam instruments combine an ion source with an SEM beam, enabling the operator to manipulate the near surface and image the results. We have two focused ion beams, or FIBs. Our FIBs are primarily used for preparing specimens for transmission electron microscopy and atom probe microscopy, nanolithography, and cross-sectioning. A cool extension of cross-sectioning is the technique of fib tomography, which uses successive cross-sectioned images to produce 3D renderings of hard and soft materials. In addition to SEM imaging, we also use transmission electron microscopy to study biomolecular systems. TEM allows us to study details of the ultrastructure of biological specimens, including cells, tissue, whole organisms, and plants. Cryo-electron microscopy allows researchers to study soft material systems in single particle analysis and structural biology in their native physiological conditions. Our introductory TEMs allow users to learn how to operate the instruments and are also excellent workhorses for routine TEM analyses. We also have more specialized instruments for advanced imaging and analysis. For example, we can study real-time dynamic imaging via in situ studies, our CS-corrected STEM allows us to study materials at ultra-high resolution. In addition, we can study the elemental composition of the materials through a combination of EDS and/or EELS mapping. Also available is the technique of 4D STEM, in which we use diffraction patterns at each point to map out different effects such as polarization mapping, changes in the diffraction pattern, and changes in the electric field. Our newest microscope is custom designed for Harvard's quantum engineering research needs. In fact, it's so new, it's still being installed. In addition to the techniques already shown in this video, it can also do holography. Atom probe tomography is a method in which field-evaporated ions from a sharpened specimen are analyzed by a precision-sensitive single particle detector. This allows us to produce an isotopically resolved three-dimensional representation of the real space specimen elemental distribution. In a nutshell, this technique can be described as three-dimensional reconstructed time-of-flight mass spectroscopy. Atom probe tomography gives sub-nanometer composition and structure resolution with parts per million sensitivity across the whole periodic table. It's a great technique for studying bulk composition, interfaces, grain boundaries, composition fluctuations, precipitates, dopant clustering, and so on. This concludes our summary. If you would like any more information on any of the techniques we've described, please contact us. Our details are available on the CNS website.